This one problem. So when we left Grey's Anatomy, we were talking about this problem, right? So we want to come up with the equation of the tangent line to this curve. So this is where we have x as a function of t and y as a function of t. This doesn't even show up in the textbook, but I wanted you guys to see something like this. Right? What this would be used for, and I pulled up my little example yesterday, and I'll pull it up again today. I pulled it up and I lost it once yesterday, as I recall. I lost it along with my x to the sixth.
At least you didn't spill monster energy drinks on all of your work. Did you? No, our coach did. Oh. Now we have to do more workouts. That's kind of fun. No, it's not kind of fun because that means that he's just going to make up some stuff that's like crazy.
Because when he had set on like Chris would go harder, but we'd be decent. But now he's like, you know what? I feel like today we should just like go all out. We should go for your arms.
Yeah, so it's really
One breath.
It's really going to depend on how much caffeine you have that day. Because if he's had a lot of caffeine, if he's had a lot of caffeine, he's going to probably be like,
Wow, he's gonna be like, yeah, it's so good day today. I'm gonna be like, but he maybe didn't.
yeah.
If he doesn't have caffeine, then wait, he can have that.
Why would he not be
Because
with
we're
that?
asking about
What? What does that have to do with caffeine?
no, if he just doesn't eat ham.
What does that have to do with caffeine?
Yes.
Maybe it's because ham is disgusting.
Apparently.
Why would
Don't eat
you?
ham.
All right, so here we go. So remember yesterday we looked at this. Everyone have a glance up here, please. So if we look at a graph of x as a function of time, so all I'm doing here is I'm just going to graph the point t over pi plus 3 is the x coordinate and 0 is the y coordinate. And I'm going to animate this where we're going to choose values of t that are going to increase from -6 to 6. And so we're going from, -6 seconds to +6 seconds. This is the problem right up here, right? So this is just graphing. This is what x is doing, right? X is changing. X is a function of t. So as t increases, x increases. Right now it's going backwards, but if we just go from -6 to +6, nothing so mysterious, right? X is just increasing with time. So the x coordinate is increasing with time, right? Remember, what we're really trying to do with this is we're trying to come up with the equation of a line tangent to this curve, right? The curve, y is a function of x. We're going to graph this thing. But this is just like talked about yesterday. This would be like taking a viewpoint, looking down on this particle that's moving in the xy plane. If you're staring straight down at it, you can't resolve its vertical motion. All you can see is its horizontal motion. So imagine that we've got this particle that's, it's point-like, so we can't see any size to it, but it's lit up. And so we're watching this thing, move. Even if it's coming up towards us, we wouldn't be able to see that, right? We wouldn't notice any difference. All we see is the horizontal motion. If I isolate the vertical motion, then I'm just going to look at the point with an x coordinate of 0 and a y coordinate of sine t, right? And I'm just going to let the animation go, and you can see that one's, as t increases, it kind of bobs up and down. Which doesn't surprise us because it's a sine function, right? And then if we superimpose both of those, look at both of these at the same time. Now imagine that we combine both of these viewpoints. So we're looking down from above, and we combine that with looking from the side and isolating the vertical motion. If we combine those in one point, what is it going to look like? Notice the red and the blue makes the purple. How about that? It just looks like that, doesn't it? So there's the motion. And we wanted to find out what at pi, so that's right about there. This thing is increasing at pi. you see it's kind of moving up probably towards a peak of a sine curve, right? So if we wanted to graph that tangent line, why don't we what?
Can't you just put pi in?
Well, we could. If I put pi in, all it's going to give me are the coordinates of that point, right? Everybody agree? Okay. But that's really not what we're asking for. What we really want here is we want to know what the slope of the tangent line is. We can see the coordinates of the point. There's where the point's going to be. But it looked like it was kind of moving upward, and so something like that roughly is going to describe the tangent line. Okay. So how are we going to get that? So we've seen a visual of this. Now we don't really need that anymore. Now we want to just do the calculus, right? If we want to come up with the equation of a tangent line, what are the two ingredients of a tangent line or any line? Point and slope, right? So the coordinates are going to be, well, we know that x of pi just equals pi over pi plus 3. What's that? 4. So there's the x coordinate of the point of tangency. Y of pi equals sine of pi, which is what? 0. Okay. So the coordinates are going to be, the point of tangency is going to be at 4, 0, right? Now I got to come up with the slope though, right? That comes from the derivative. The slope of the tangent line is just going to equal dy dx at t equals pi, right? See that? So none of that's very mysterious, except how do we come up with dy dx? Because we don't have y as a function of x. Okay, so this is like the last example we did, right? The example we looked at immediately before this was one that was a little bit easier. We had y as a function of u and u as a function of x. And so we can just use this version of the chain rule, right? dy du times du dx, you know, the u's would cancel. This one's a little bit different. Now we can calculate dy dt and dx dt, right? Everybody see that? So here I've got y as a function of t. So dy dt is what? Everybody agree? Derivative of sine t would just be cosine t. What's dx dt? What, you guys trying to use quotient rule? Okay, but do we want to use the quotient rule?
It's just 1 over pi.
It's just 1 over pi. Yeah. Yeah, because look, this is really just the same thing. All I've got is a t to the 1 there, divided by pi. It just is the same thing as saying 1 over pi times t plus 3, which is a constant, right? So if I write it that way, x of t equals 1 over pi times t plus 3. Well, that's a constant. The derivative of t is 1. So we're left with 1 over pi plus the derivative of 3 would be 0. Okay? So now how am I going to combine those? I've got a dy dt and a dx dt. Right? Flip it over, right? Just flip and multiply. Okay? Or if I want to think about it this way, I could also even make it, I could do dy dt divided by dx dt. It's the same thing, isn't it? Right? If I divide those, that's equivalent to dy dt times dt dx, right? Either way, it doesn't matter. Either way, aren't I just going to get cosine t times the reciprocal of dx dt is going to be times pi, right? I have a chain rule. Kind of a fancy version. I mean, like I say, this is not stuff that even shows up in the calculus book, but it's stuff that I think is kind of important to see at least once this year. Well, if dx dt is 1 over pi, is dt dx pi? Right? So look right here. If dx dt is pi, then its reciprocal, dt dx, is pi over 1,
Yeah.
right? That's what that is. Does that make sense? Yeah.
Wait, and is that's our line?
That's the derivative. That's dy dx.
Wait, that's the slope or the?
That's the slope. dy was the slope function. dy dx is given to us by the chain rule, right? We gotta get the t's to cancel. Right? We can take the rate of change of y with respect to t and the rate of change of x with respect to t. We can multiply those in the right way so that the t's cancel. Okay? It's like the clock example we did. Remember the clock example? We had the analog clock. We had the rate of change of we had the position of the second hand, right? The rate of change of that. We had the rate of change, or the minute hand with respect to the second hand. No, second hand with respect to minute hand, and minute hand with respect to hour hand, right? They were separate rates, but then we were able to combine those together to get the rate of change of the second hand with respect to the hour hand. Remember that? Okay. And just like that example, right? We had y with respect to u and u with respect to x, and so we can, by the chain rule, dy du times du dx is going to give us dy dx. Okay. Only this time instead of a u, it's a t, right? Okay, so that's a little bit of a weird one. This one's not. This is pretty straightforward. So this time we're given an explicit function of x. Y is an explicit function of x. And so this is something that you see in the calc book, right? In the first year of calc book. So if we want to find the equation of the line tangent to this curve at x equals 1, if we want to find a tangent line, just like always, we need a point and a slope, right? So what's our point of tangency going to be this time? What's the x-coordinate of our point of tangency going to be? 1, yeah. And to get the y-coordinate, what would I do? Plug it in. So if we evaluate the function when x equals 1, we're going to get 2 times e to the 1 minus 1, e to the 0. What's that? 1. So I just get 2 times 1 is 2. Right? So there's my point of tangency. Now I got to find the slope of the tangent line. But that's always going to be, that's what the derivative function does, right? It tells us the slope of the curve. So the slope of the tangent line is just going to be y prime at x equals 1 in this case, right? If I differentiate this, what do I get? What is y prime? Got to use the only difference between this and the previous problems that we've done in past sections is now we just need the chain rule. It's the same idea, isn't it? So what's the derivative of, what do I do with the 2? Just leave it out front, right? Now I've got the derivative of e to the hand. What's the derivative of e to the hand? E to the hand. So the first layer is going to be, I've got my 2 out front. The first layer is going to be e to the hand. But I got to look inside the exponential function and take the derivative of hand. What's that going to be? Right? Because I've got layers to that function. So if we pick apart that function, the exponential part, first layer is an exponential. The second layer is going to be what's inside the exponential. Right? So there's the first link, there's the second link in the chain. So we end up with what? Negative 4x e to the 1 minus x squared is our derivative function. That its job is to tell us the slope of the curve, right? At any value of x we choose, well, we choose 1, right? So we're just going to get -4 times 1 times e to the 1 minus 1 squared, so that's just e to the 0, right? So what, -4? Yeah, it's easy. We got the slope of the tangent line, we got the point of tangency, we just combine those and make a line. Okay? Right? So all we have to do is just do y minus 2 equals m times x minus 1. And that's the answer. I mean, we could simplify it if we wanted, but that's the equation of the line. Okay. All right, so then all I really want to do, and that gets you up through, I think, there's a ton of, 2.4 is huge. The chain rule stuff, I mean, there is so much stuff lumped into there. I'm just breaking it into small pieces. But that's like the 4th assignment, I think, from 2.4 is this stuff, right? It's just kind of getting a little practice with tangents to curves. That's something that's a big topic in first year calculus. So then it goes into, it adds another, the next thing we kind of approach in 2.4 is it talks about derivatives of log functions. Okay, but before we even do that, I want to take a chance and just not even worry about calculus. Let's just take a day and let's just review log functions a little bit. It's probably been a while. I'm sure they're not super fresh in your mind probably, right? So let's think about logs, let's think about properties of logs, because they're really important in calculus. So let's just, what does a log function look like, first of all? If I have f of x equals, let's do natural log x, what's that look like? And kind of, what's the shape of the curve, though? No, this one's, there's a way we can always, rather than just me tell you, I'm going to show you, remember what an exponential graph is like, right? That one starts on the asymptote, so if the graph e to the x, it just looks like this, right? Not the reciprocal. So that's y equals e to the x, and it crosses at the point 0, 1, right? And it's asymptotic on the negative x-axis, okay? So you've already kind of told me some of this stuff, I think. Didn't we talked about logs a little bit at the start of the year, didn't we? A little bit. I think you all told me this. You told me that if I write this with y, what's an equivalent way to say that? Because what's the implied base here? No? E. E. If it's a natural log, the implied base is an e. So what's an equivalent way to write that? No, almost. E to the y equals x. Did we not review that?
No.
We haven't talked about that this year?
No, maybe we need to put this on pause and we'll get a separate short meeting on pause.
Okay, I'll just keep going with it, but this is going to be, we'll talk about logs here. So one thing, you can always, if I have an exponential statement, I can always write an equivalent, or a log statement, I can always write an equivalent exponential statement. And there's a really easy way to remember this. You can just remember the sentence, a log is an exponent, which would probably evoke some quizzical looks if you were at like a forestry conference or something, but it's valuable to remember in math. A log is an exponent. So whatever the log is equal to becomes the exponent, right? The base of the log is the same as the base of the exponent, right? So we end up with the statement, the base e to the y, that's the exponent. The log is equal to the exponent. A log is, aka equals, an exponent. E to the y equals x. Those say the same thing. Okay, so for example, what if I had something like y equals the common log? What's the equivalent statement for that?
y equals x.
Yeah. Okay. 10 to the y equals x. Okay, those are equivalent statements. How do we, what happens if we, how do we create an inverse relation? What's it mean to be an inverse? At the basic root of something, if I want to talk about, I give you a function, I want you to come up with the inverse function. Let's just practice this a little.
That we switch the x to the y, and then we solve the y.
Okay, everybody agree? So if we do something like what if we started off with, something like y equals 3x plus 2? Just take something simple like a line. If I want to find the inverse, all I'm going to do is flip the x and the y, right? And solve for y. So I would just subtract 2 and divide by 3. So y is going to end up equaling x minus 2 over 3. Agreed? Okay, if both of those are functions, then it's a one-to-one relationship, right? You get, if you've ever talked about this back in, we did this a little bit at the end of Algebra 2, you would have done a lot of it last year probably, right? Freak out. Okay, what would happen if I were to, well, I'm just going to do the full review of this. I think you guys, sounds like you, I don't know, people, raise your hand if you feel like you need a little review, or like maybe a little more than a little review of logs. Okay, we're going to do the full meal deal here. All right, so if we call this, if I'm going to make one little change to this then. So if we call the original function f of x, right, and we calculate the inverse, and we're going to call the inverse g of x, how could I verify that those are inverses?
If you plug it in, then you end up with 0.
Not 0,
Yeah, well,
x.
x.
Okay, they undo each other, right? That's what inverses do, is they undo each other. So if I did a composition of these functions, and it has to work both ways. So if I did something like f of g of x, that has to equal x. Let's just show that it does. Well, f of g of x is going to be 3 times hand. F of hand is just 3 times hand plus 2, right? But hand is, in this case, g of x, which is x minus 2 over 3. Well, what's going to happen if I simplify that? The 3's are going to cancel. X minus 2 plus 2 is what? X. Okay, so it works. I get x. But it has to work both ways for these to be inverse functions. G of f of x would also have to give us x. Well, we could do that one. So g of f of x is what? G of hand is hand minus 2 over 3, right? G of hand is hand minus 2 over 3, but this time hand is f of x. So it's 3x minus 2. Well, not surprisingly, the 2's, this is plus 2.
Yeah.
Okay. The 2's cancel, and then I get 3x over 3, which gives me my x. So those are indeed inverses of each other, inverse functions. Okay? Just while we're on the subject here, this is kind of a deal. So what's the inverse of x squared? If I pick f of x equals x squared, we're going to say g of x is the inverse. What's that going to be? Okay. Everybody agree? Let's try it. If that's true, f of g of x has to be x, and g of f of x has to be x. Okay. So f of g of x would give us f of x is hand squared. So we're just going to get g of x, the square root of x, squared. Yeah, it works. It's equal to x. Okay, so far so good. What's g of f of x? Well, g of hand is the square root of hand. Well, this time, hand is f of x. So I get the square root of x squared. What's that equal to? Ah. So So those are not inverse functions. Isn't that kind of weird? Why are those not inverse functions? Let's prove it. If I were to graph both of these, if I graph f of x equals x squared, it looks like that. If I graph g of x equals the square root of x, what does that look like? Okay. It just looks like that. It worked, right? Okay. We could have predicted it wasn't going to work, though, right? You can't take a square root of a negative number, right? And does this remind you about the symmetry of the graphs of inverses? Yeah, and we can prove that pretty easily too. Because I'll say this in a way so you'll remember this forever, right? If we're going to take, you told me that the recipe for building an inverse is to switch x and y and solve for y, right? Okay, but the key ingredient there is you're switching x and y. That's what really did it. I mean, that's the true definition of an inverse, is that it swaps the domain and the range. You interchange the domain and the range. So if I've got some random function, and let's just say I know one point on that function, if that point has coordinates, let's call it x1, y1, what's going to be a guaranteed point on the inverse function? y1, x1. Let's even put some numbers in there. I think that's going to be easier to do. Let me just pick some, I'll just make up some numbers. So let's say the coordinates are 5, 2. A guaranteed point on the inverse function is going to be 2, 5. Agreed? Was there anything special about that point that we picked? No. It's just an arbitrary one of an infinite locus of point, infinite set of points on this original curve. So I should be able to do the same thing for every point, right? But you see that there's going to be this one-to-one correspondence for every point I choose on the original function. There's going to be this partner point on the inverse function, right? And what do you notice about the symmetry there? Well, yeah, look, it's just reflected over that line y equals x, isn't it? Right? That's all it is. And so that tells us that guaranteed, because I picked a random point and it worked, it has to work for every point. That's kind of a distillation of a mathematical argument we could make more formal. But that does the job. I mean, that tells us that everything we need to know, right? And so then if we go back and look at this graph here, doesn't work, right? We don't have that one-to-one correspondence. This lobe of the parabola over here didn't get reflected. This one did. But that guy didn't. If it did, look what would have happened. We would have ended up with something like that, and that's not a function. Is this ringing a bell a little bit?
Yes.
Right? So we could have predicted, though, that the inverse of this parabola was going to fail the vertical line test because the parabola fails the horizontal line test. Is this coming back a little bit now? Okay. All right, so let's go back to logs then. So we've got this. We know if I were to, so let's derive the inverse of the log function real quick. Easy to do. Same recipe you already told me. We're just going to write it in terms of y, swap x and y, and solve for y, right? So we're starting here with f of x equals log x. Let's make that y equals log x. Here's that little base e, right? So all I got to do if I want to find the inverse is swap x and y. Okay. I want to isolate the y there. Well, what could I do? Yeah, I could just write the equivalent statement, couldn't I? Write that logarithmic statement as an exponential statement. A log is an exponent. So my base is e, right? So e to the x. The exponent is the log. Whatever it's equal to is the exponent. Equals y is the same thing. We just proved it, right? These are inverses. We proved it by just flipping x and y and solving for y. Right? So if they're inverses, then what does the graph have to look like? What's gonna be,
X equals a.
yeah, so this point right here with coordinates 0, 1 is gonna map onto the point with 1, 0, right? Point with coordinates 1, 0. And this asymptote is gonna map onto this asymptote if I pulled it over that line, right? And so isn't it just gonna do that? So there it is. Yeah, y equals log x. See how that all kind of wraps up neatly together, how it all relates? Just love that. It all just comes together. Right? It's all the same stuff. What's another way, and I don't want to bore you with too much of this, but there's another way we could, now, I won't get to that yet. We could, there's some algebra, I'm gonna hold off on this one. So we got we know what a log curve looks like. Now let's review some properties of logs. Okay, there's 3 important properties of logs. And you probably remember, hopefully remember talking about this a little bit in Algebra 2. Remember the ladder analogy from Algebra 2? That logs make things one rung easier, you step down the ladder one rung? Not so much. Okay, well, we'll hear it again. So here are the 3 properties of logs we have to remember. If you think about kind of an order of operations hierarchy, think about your order of operations tree, right? You've got parentheses, we'll skip parentheses, but we've got exponents, multiplication and division, and addition and subtraction. We sort of step up in complexity from the bottom rung on that ladder to the top rung, right? The properties of logs always drop you down one level. Okay, so for example, you fill in the blank here. The log of A times B equals what? Yeah, it's going to take you from a product to a sum. Okay. The log of A times B equals the log of A plus the log of B, right? Drops you down one. And this, I'm talking about using this language because this is the language this is going to be really critical to us in calculus. We're going to turn around here in a couple days and we're going to use these properties to make hard calculus problems a lot easier. There's a technique called logarithmic differentiation I'm going to teach you this. It's really, really valuable. So what about something like this then? What about the log of a quotient? Remember what that is? Good. And look what we did. We went from division to subtraction. Okay. And then the last one, what about this? The natural log of A to the n. No? Remember this one? What we do with that exponent? No, don't do anything fancy like that. This is just a simple property of logs. Well, what do you think it's, make a prediction. That's an exponential expression, right? It's going to drop us down a rung, so where should it go from exponential? It's going to drop us down to a product instead of an exponential. All you do is you just pull that exponent out front, and it equals n times log of A. You remember those? That ringing a bell? Okay. So let's just practice those a little bit. That first assignment just kind of covers this stuff. So we could do, like, let's just do some practice problems. How about if I give you, I want you to simplify, start easy here. Don't say it out loud. Everybody just think about this on your own. So what is that? What is that? Okay, so natural log minus natural log, natural log 2 minus natural log 3. So we could, in many cases, we could take just a handful of specific log values, and we could use those to simplify lots of more complex logs. What about one like this? What if I had natural log of 1/2? What's that? Right. So it's natural log of 1. And just so you know, I mean, when you go to college, you're not going to say ln. You want to say natural log. It'll sound like a doozy if you say ln. You want to say natural log. natural log of 1 minus natural log 2. And natural log 1 from our graph is what? It's natural log of 1 is 0, right? Good? Okay. Did you guys, is that what you guys called it last year?
She called it outline, yeah.
Oh, well, it's, I mean, I'm sure it's okay, but just so you know, you guys, just don't do that in college. That's,
Don't do it in professional settings.
yeah.
And what do we call the other one?
Log.
You just call it log. Yeah. Well, and you could, I mean, really, like, I would just, if it's implied we're talking about natural logs, I would just call that a log, right? I mean, usually there's gonna be a context where either you're gonna be a base E exponential, like for natural growth, right? That's really what this would be for.
You think you could put like, practice this?
I did, yeah, that's the first assignment is not calculus at all, it's just practicing this stuff.
Okay.
That's all it is, yeah. So natural log of 1 is 0, so that gives us negative log 2. Do that a different way for me, please.
1/2 is the same as 2 to the negative first.
Okay.
So take the negative one and cut to the top.
Everybody see that? Right, so we could just pop that negative 1 out front and get the same answer, right? Okay, what about, and try this on your own, everybody, try this real quick. What if you had something like, be careful with this one. Trick. That's different than,
Let's just keep that one out.
it's different than that.
Yes.
Everybody get that? The implied parentheses here would be around the x to the 4th. So this one would be 4 log x. This one is nothing. It's just what it is. There's not, you can't simplify that. Okay? Pretty tricky, huh? Pretty tricky. What is that? Maisie, what is that?
Oh my god.
The one had the top two and then, add top two.
Yeah, right. So that's going to be, I'm just going to get the log of the numerator minus the log of the denominator, right? But the log of the numerator we could actually write as log x plus log y. So it's just that.
What would the answer to the log x to the 4th?
Okay.
Wait, can we not do the other one?
This one you can't do anything with
Why?
because it doesn't fit any of
No,
our,
it's not MDAS.
yeah, it doesn't fit any of our stuff, right?
MD says.
It's not what? Okay. Oh, okay, here's a good one. Okay, what about this guy? Let's do this step by step. What's the first thing we could probably do to this?
Take the 3 and move to the front.
Take the 3 out front, okay? So we get 3 times the natural log of x squared minus 1 over x cubed. Time flies.
Back to that next step. Next week, some concepts.